Welcome to our exploration into the impacts of artificial intelligence on the environment. Most of what we will cover in this research project is the impact of artificial intelligence data centers, since that's the physical manifestation of AI. Our driving question for this research is, how do the resource consumption and carbon emissions associated with training and deploying large-scale artificial intelligence models compare to traditional computational methods? And what strategies can be implemented to mitigate their environmental impacts?
First, we'll be looking at the resource composition and how AI plays into energy and water use. As artificial intelligence continues to evolve and integrate into every aspect of our lives, we have been seeing a rapid change, mostly in the aspects of energy demand and water use. AI and server energy use. Over the past decade, we have witnessed a massive transformation in server energy consumption, specifically driven by the rapid increase of AI. Back in 2014, more than 60% of server energy consumption came from internal data centers. These are more private on-site facilities owned by individual companies. However, within 2023, the number decreased by 10%, and a lot of industries shifted their energy consumption, specifically to more hyperscale and colocation data centers. These large-scale facilities are mainly owned by Google, Amazon, and Microsoft, and a lot of them utilize AI. And within 2023, nearly 80% of servers are said to have used this type of energy consumption, and the number continues to grow. By 2028, it is expected that over 90% of all energy will flow through this type of consumption, and this is largely due to AI workloads. This graph just shows the change in AI and also really looking into the range of AI and consumption use. After 2023, the projections show a big range of possibilities, specifically based on how many servers are deployed, how effectively they run, and how often they are operating. Some servers might run at 60% of their rated power, while others reach about 80%, and the operationalized time may be from 75 to 85% per year. These variables result in a wide estimate of the total server electricity use by 2028. And predicted in 2028, on the low end, we see about 240 terawatt hours of consumption, but on the high end, we can see up to 380 terawatt hours of consumption. Regardless of either scenario, both are a substantial amount of increase of the general total annual server energy consumption. So the overall demand of AI is going to be exponentially increasing as time goes on, and is what we've seen prior in these past years, and something that we're going to be looking at in 2028. A lot of the conversation with consumption, usually with AI, comes around electricity. However, the water footprint is often overlooked and might even have a bigger implication than electricity. Under Scope 1, we see water being used in data centers, and this is primarily for cooling. But high-performance computing infrastructure generates a lot of heat. And because of that, there needs to be a lot of water-based cooling systems that usually were not seen prior with other internal computer systems. Specifically with Microsoft, as an example, they saw a 34% increase in water use in just 1 year alone, and that was to support systems like ChatGPT. So already there is a huge shift with utilizing AI and just the cooling process. Under Scope 2, we see water being used during electricity generation. So generating, producing the energy needed just to run the AI servers, and also a lot of this water is pulled from natural ecosystems. To put that into perspective as well, just to power a single 100-word email through ChatGPT, we use approximately 519 millimeters of water, which is around a standard water bottle. When we scale this up globally, this is projected to reach a withdrawal level of about 6.6 billion cubic meters. And this is around 2027 alone is when this scale is projected to happen. So we see that there is a real environmental cost with AI and the upscaling of AI. And with these computations as well, AI has overall relied heavily on just the accelerated servers, more heavy duty servers, which require more power and also more advanced cooling systems. As we're going to talk about in the future, this can also have implications on carbon emission, water withdrawals, and just the upscaling of AI in general. So it's important that we understand and manage the resource demands that come with AI and the changes from more traditional standard models that we are used to rather than AI.
I now want to shift our focus to one of the most significant environmental consequences of that energy use, carbon emissions. What makes this issue so urgent is the scale. These large AI models, like GPT-3, require massive computing power, and training them can emit hundreds of tons of CO2, which is equivalent to the lifetime emissions of several gasoline-powered cars, and that's only for training. Once these models are deployed, they continue to use energy to serve millions of tasks daily, which add even more emissions over time. Understanding the carbon footprint of AI helps us ask smarter questions and how we build and use technology. Before diving into AI, let's break down what carbon emissions actually are. Carbon emissions, mainly carbon dioxide or CO2, are gases released when we burn fossil fuels like coal, oil, or natural gas. These are fuels that power things we use every day: cars, factories, airplanes, and importantly, for this presentation, computers and data centers. CO2 itself isn't harmful to breathe, but it has powerful effects on our atmosphere. It traps heat, sort of like a blanket wrapped around Earth, which causes global warming and leads to climate change. More emissions mean rising sea levels, more extreme weather, wildfires, and also long-term environmental damage. So reducing emissions is one of the biggest challenges and responsibilities that we face globally. This is where technology like AI comes in. It's growing fast, and while it's useful and innovative, it also consumes so much energy. That energy use translates into emissions, depending on where the power comes from. Now let's put everything together. How does AI actually contribute to carbon emissions? When we train large AI models, like for example ChatGPT or image generators, they run on massive clusters of computers and data centers. These models require billions of calculations, and training them can take weeks or even months. That process uses a ton of electricity. If that electricity comes from fossil fuels like coal or natural gas, then a lot of CO2 is released into the atmosphere. For example, training GPT-3, which is one of the largest language models to date, was estimated to emit over 280 metric tons of CO2. To put that into perspective, that's similar to driving a gas-powered car more than 700,000 miles, or what 5 average cars emit over their entire lifetimes. And this isn't just a one-time thing. As companies continue to retrain models, release new versions, and expand AI into more industries, the energy demands and the emissions are only increasing and going up. So let's look at the actual numbers behind this. So this chart right here shows the approximate CO2 emissions from training several well-known AI models between 2015 and 2022. You can clearly see that emissions have only skyrocketed, starting at under 1 ton for small models and then jumping to over 280 tons for GPT-3. Why is there such a jump? Models are only getting more powerful, which means they're using more data, more parameters, and more computing time. It's like the difference between charging a phone and powering an entire city block. So GPT-3, for example, consumed almost 1,300 megawatt hours of electricity just during training. That's enough to power the average US home for over 120 years. So these trends are telling us something important, and we really do need to start listening. As AI evolves, we have to be just as innovative with how we power it. Otherwise, we risk creating a technology that, yes, helps us solve problems, but is also adding to one of the biggest problems we already face today, which is climate change.
So let's see how an AI query compares to a normal Google search or a Google search without the new Gemini AI feature. Then we'll compare current AI power consumption with that of the future. The release of OpenAI's earliest ChatGPT model on November 30th, 2022 was estimated to require about 10 times the electricity than that of a normal Google search. That's a change from 0.3 watt-hours for a traditional Google search to a 2.9 watt-hours for the ChatGPT search. And even then, AI is expanding exponentially. Now with more complex response synthesis generation of original music, images, and videos based upon user prompts, new AI applications are requiring much more power that hasn't even been reported on yet. With about 5.3 billion global internet users, widespread adoption of AI will require exponentially more power. Now, all of this AI processing happens in data centers. The growth of data centers is projected in these 4 scenarios. Each scenario counteracts the technology efficiency increase, namely the annual -1% to -2% influence on the global energy consumption. Here are those growth scenarios charted so we can visualize this exponential increase. The highest growth scenario estimates that by 2030, data centers could consume up to 9.1% of U.S. electricity generation, an increase from today's 4%. That is a huge demand that needs to be mitigated. Now, since history has shown that demand for increased processing has largely been offset by data center efficiency gains, we have to find ways to make the AI algorithms more efficient so data centers can have time to catch up in terms of technology efficiency. The first technique to do that is pruning. Pruning is a process that happens naturally in the human brain as you go into adolescence. Neural pathways selectively die as you develop and get used to your environment, so you specialize and become more efficient based on the environmental demands in your life. Incorporating pruning into AI models is needed to increase processing speed and decrease memory storage that isn't necessary. Quantization can also decrease the size of a model. It is converting large point numbers like 32-bit to a lower precision number like an 8-bit or a 4-bit. This reduces model size and memory requirements while also potentially improving computation speed and energy efficiency. Then coding an AI model routing system to select an AI model that is best suited for a specific task or inquiry could reduce unnecessary usage of oversized models for simple tasks. Finally, the simplest technique to reduce AI's power demand is decrease the usage at the source. Companies should place a premium on AI usage, charging subscriptions for use to decrease public usage and AI power demands. Since data centers require immense computer cooling, and the cooling is a large factor in energy consumption, we need to consider that liquid cooling is the most energy-efficient method. The leading AI companies now use water or liquid cooling, including NVIDIA, OpenAI, Google, Microsoft, and Amazon, but Meta still uses air conditioning method to cool data centers, which is problematic because air cooling a single chip requires extremely high velocity fans and significantly more space. This increases energy demand by 50% compared to a liquid-cooled data center, in turn increasing emissions and producing much more noise pollution. Like I said, liquid cooling uses less electricity than traditional air conditioning or air cooling systems. A recent study which had analyzed the shift from 100% air cooling to a combination of 25% air cooling and 75% liquid cooling observed a 27% reduction in facility power consumption and a 15.5% energy decrease across the entire data center site. As I mentioned with the growth scenarios, since AI is projected to consume up to 9.1% of all energy in the United States, we need to shift how AI data centers interact with the grid. The EPRI report talks about this a lot and suggests shifting the data center grid relationship from the current passive load model to a collaborative shared energy economy. This means that data centers would contribute to the grid rather than just extracting energy as needed. This would work with a combination of data center backup generators, independent power generation with renewable sources, microgrids, a demand response, which means it would take less energy from the grid during high energy demand periods, and then energy storage. So this would be in batteries during low demand periods that could feed back into the grid. The combination of these things would make a more reliable grid while reducing the cost of data center operation over time.